Hey, today I want to talk about the camshaft and valve systems. In the first chapter, we model a crankshaft. Following chapter, we use the output of that model to calculate the position of the piston. And now, we will compute which valve is open and specifically how much open that valve is. If we simplify the black box model, we want such a model that it takes the crankshaft angle and gives us how much the valve opens as an output. We keep in mind that and start modeling with the Desmos, because it's perfect online tool to play around with the graphs. I wanted to start the modeling by preparing the cam profile, because the camshaft is connected to the crankshaft and we already know the camshaft angle and angular velocity. Let's start with e to the power of x. It's gradually increasing, which means that if we plot the e to the power of minus x, it will gradually decrease. This behavior is suitable as an input signal, but we have to combine them. To do that, we can use e to the power of minus x to the power of 2. Now, the valve is open and closed, but the opening and closing times are too long. To make it more aggressive, we can choose high power of x. Now it's look like a proper shape. But the thing is, cam profile is circular, not linear. We can redefine it in the polar coordinate system to make it circular. But before that, because circular shapes are defined in the range from 0 to 2 pi, we put a reference line to the 2 pi and shift the signal to the right. Lastly, we know that this cam profile is for a 4-stroke engine, and if we use 2:1 U ratio for the camshaft, the valve should open and close within a quarter of the cycle. We will see that in a minute with the animation. So the signal should shrink to the quarter of the rotation, and here we have it, the equation of simple cam profile. You can make it more realistic and complex, but it's enough for me as a beginning. Let's redraw the equation and convert it to the cam profile. All we have to do is change the x-axis with the angular coordinate and set y value to the radius of the polar plane. Because our equation gives just an offset, we sum the value with the camshaft radius, which is 2. Now it's look like a cam. Let's see how it works right away. After placing the slider crank mechanism, cam profile, and valve, we should adjust the timing. We define the crankshaft zero angle as so, and the piston moves down first for increasing angle. Then if we choose the valve as an intake, we can set the starting point of an intake cam as shown in the figure. And remember that we use 2:1 ratio for camshaft rotation. Everything is ready and we can start the engine to see the results. As expected, the valve opens at the start of the intake stroke and closes right before the compression stroke. Power, exhaust, intake, compression, power, and so on and so forth. The good thing is it works. The bad thing is it shouldn't work like that. In the real Valvetrain, the cam lobe isn't always in contact with the valve. Instead, the valve returns with the help of the spring. This means that if the crankshaft turns fast enough, the valve may separate from the cam lobe, as seen in the animation. Modeling that behavior linearly is not as easy as modeling other dynamic systems. We took some time with Hamza Köse to model this system as simple as possible, yet working properly enough. By the way, Hamza is super intelligent and helped me a lot in that project. He also running a YouTube channel about Kerbal Space Program. If you like simulations and physics, you should check them out. If we consider cam-valve interaction as a mass spring damper system, the valve position can be modeled as a point mass. The blue dot represents the point mass, and the white rectangle is cam input. When the cam squeezes the valve spring and releases it immediately, it should behave like that. But you notice that the valve is gone through the cam, which is not intuitive. To solve that, what we came up with is tracking the position of the rod and cam input to detect whether they are come into contact or not. If they are in contact in the following sample, we invert the velocity of the valve in the state vector with respect to the elastic collision. Before the elastic collision, we model the system as linear with state space. The x dot vector carries velocity and acceleration states. The A matrix is the same as the one we calculated in the first chapter because it was also a standard mass spring damper system. The x vector stores position and velocity states. Because there is no external input force, the last terms become 0. Also, no need to calculate y because we will use the states vectors directly. The equation is simplified as so. But as we said earlier, we cannot use that model because it will not interact with the cam loop. But we have a solution. Let me explain it in the Matlab Simulink environment. Let's focus on cam dynamics. X substring E stands for displacement input from the cam loop. Preload is the initial spring compression amount, and X substring R is the real displacement value of the valve. Down here, the state space model is the same as the linear model, but the difference is in the integration part, which is here. Firstly, we calculate the temporary position to know whether the output exceeds this input. If not, we take the integral as it's supposed to be. If the valve contacts the cam, the position is set as the cam input position, and the velocity is recalculated with respect to the elastic collision. By the way, we assume the cam input has infinite mass, so every time the valve collides with the cam, its speed is reversed. X substring I substring D is the velocity of the cam, and this 0.5 is energy loss caused by the collision. The other two if and these are just for initialization. Input velocity is calculated with this equation. X substring I substring L is the previous input and set it here. The valve's actual position is the first term of the X state vector. Other blocks are not as complicated as it seems. The crankshaft block comes directly from the chapter 1 and calculating the position and velocity of the crankshaft with the given torque value. The first element of the derivative of the state vector is crankshaft velocity in radians per second. If we multiply it with this constant, we can get the RPM. This block comes from chapter 2, calculating the piston position with respect to crankshaft angle. Remember we said we use 2:1 ratio for camshaft rotation. So this block reduces the rotation. In this section, we model the camshaft angle and add phase to the exhaust cam. In the cam displacement section, we generate the input signal with the equation that we calculated. The only difference is I scale the input and add a preload value. We already talked about the cam dynamics. Lastly, the valve opening is calculated with that equation. We assume the opening area is the area of the side of the cylinder created from the valve's displacement. That's it. Now we know the piston position and the opening of the intake and exhaust valve with only feeding the torque value to the system. Let's run the simulation and discuss the results. The engine reaches around 4,400 RPM at the end of the simulation. In that scope, the piston oscillates as expected. If we zoom in on a section of valve position, we can see that the valve is able to follow the camshaft input. There are a few oscillations at the maximum state, but it's not a big deal. The real challenge starts when we increase the RPM. Let's go from 4000 all the way to 7000 RPM and check the valve position again. As we can see, the camshaft pushes the valve so fast that it can't follow the input in the closing state and bounces when it returns. That means the engine is loose compression and power. Let's integrate that model into the Unity. I add two valve, a cam, and some UI elements to the project we built in the chapter 2. In the discrete model C# file, I will only talk about the newly added ones. You can watch the previous chapters to learn more about the code. I added 4 new game objects for cams and valves, 3 UI elements to see the RPM, change the spring coefficient, and toggle the slow motion. Create 2 valve model from the valve class. In the valve class, there are system parameters here, matrices for state space, states, and variables for position input. The position input is calculated with the cam profile equation, preload is added, and the input velocity is calculated. Then we calculate the next position of the valve and check if it has contact with the input, in other words, the cam lobe. If there is no contact, X dot, and the valve opening is calculated. If there is a contact, the state vector is redefined with respect to the elastic collision, as we do in Matlab Simulink. The intake and exhaust valve functions are called in the loop, and exhaust valve has offset to match with the strokes. Lastly, we update the valve position and cam lobe rotation with the calculated values. That's all, and now we can run the model and enjoy watching the valves. In lower RPM, valves are able to follow the cam input as shown. But if we higher the RPM to 7000, we can barely see that the valves are floating. Of course, we can solve this issue with the stronger springs, for example by doubling the spring coefficient, but there is a physical limit for the springs, and a higher spring coefficient means a higher force is needed to compress them, which is inefficient at low RPM. That's all for the Valvetrain. In the next chapter, we will discuss thermodynamics. As always, you can find all the project files and codes on GitHub. See you in the next chapter. Stay tuned.